Janek, should we start?
Yeah, I guess we have waited 5 minutes.
Okay.
So this week we wrap up our discussion about lasers. The week three assignment was probably the one of the longest assignments, and also the one of the hardest. Like no further assignments will be as hard, I think. But to attempt those questions, first of all, you need to take notes, like get all of these kinds of formula when you encounter in the lectures. You have to make notes because all of the assignment questions are based on these formulas, and to apply these formulas you actually have to understand what these things mean. So where to apply uh, which formula. For example, these two formula look very similar, but they describe uh, like two components of the chirp. So like conceptually you have to be clear, but the questions that are asked are always based on these formulas that were introduced in the class. In this week's assignment, I think there are two formulas that are these two formulas that are not touched in class. I think in class we said Lorentzian PDF, but did not elaborate what Lorentzian PDF is. So you can get the answer directly from Wikipedia or something, but still, this was probably not included in the video, if I'm correct. Anyway, uh, this week we started with the discussion about chirp, which is change in frequency with respect to time. And we discussed different ways how chirp happens, how to quantify those. There were some formulas introduced again. Then we went on to discuss noise in laser, uh, noise in the power level, which is captured by relative intensity noise, and the phase noise, which shows some unique behavior. Uh, I hope it was not too difficult to understand. So the formulas that come from these concepts are easy, but you have to understand them properly to apply them, right? And then we briefly touched on single frequency lasers, which require some more ingenuity to like make, and the cost also goes up, of course. And then one of the most important concepts, uh, very useful for this fiber optic link design, not link design, but i- if you want to make anything, like you have to use electro-optic modulation. So those concepts were introduced, and also I hope you're familiar with this interferometer concepts from earlier, like basic photonic course might have uh, discussed it in more detail. Here we show that electric fields just add up. Uh, the, so uh, the electric field intensity in both arms add up when they interfere. Like that we are a Mach-Zehnder interferometer is what we are using as a Mach-Zehnder modulator now. And from the intensity versus applied voltage graphs you might have seen in the class, we get these peak points and quadrature points, how to identify those, uh, what is the significance of V pi, and how to make IQ modulators using these Mach-Zehnder modulators, then how commercial transponders achieve 100 Gbps from like 25 Gbps okay input signals. So that was discussed in class. These are a list of equations that were introduced in the class. If you want to, feel free to take screenshots. But uh, these won't mean anything unless you understand what uh, these quantities are talking about. So we started with this Henry's line width enhancement factor. Then using from here we go to this transient chirp. Then how this total chirp is got from there. Then from RIN discussions, relative intensity noise, we define relative intensity noise and how we describe it using RMS value, how the power spectral density of RIN is captured, and how to get back to RMS RIN from power spectral density. So those were discussed in class. There are questions from all of these in the assignment, I think. And then um, we go to laser phase noise, where we introduce this concept of phase error and line width and how to relate those two. And the working formula, the most useful formula is this one, that how line width is related to the phase error variance. Um, then we told that the laser frequency response would show a response something like this. From the full width half maximum of this comes this line width. So how to relate all these things, you have to know. There is one question in the assignment about this Lorentzian PDF, but instead of asking, they're giving you the full width at half maximum, and using this uh, formula, this equation, they're asking you where this power gets to 1 by 100 of the peak power instead of half of peak power, which is given as full width half maximum. Then we move on to electro-optic modulation. We start with phase modulation and how to use interferometer concepts to convert phase modulation uh, terms to intensity modulation and how to use it. And we also plot these curves, cos square phi curves that come on. Here I want to show a data sheet of a tunable laser we use in the lab, just to show you what kind of figures you can expect in a laser we are using in the lab for our tests. So this, you can see a line width. Line width is given as 100 kilohertz, and relative intensity noise was given as this minus 135 dB per hertz, less than minus 135 dB per hertz. So these are typical high-end lasers we use. Like, here you can set different wavelengths and power outputs what you want. Like this can go up to like from actually 5 to 15 dBm, uh, and wavelength is also tunable. In the class, ma'am showed, I think, how to make a tunable laser. And here is one electro-optic intensity modulator. The datasheet was extracted from a web page, so it's a little ugly. But the quantities that were introduced, like insertion loss, you can see typical insertion loss of 3.7 dB. So Is it readable? Like, is it too small? I hope I have not disconnected. So, an extinction ratio that goes from minimum 20 dB to a typical you can expect 27 dB in this product. And bandwidth you can support up to 10 gigahertz. This is talking about electrical. And the V pi is given as 3.1 volt. So from this you can expect that it's a push-pull configuration. So these are two data sheets I wanted to show, and this is the same cost square curve. Not ideal because this is not going to zero minus infinity in log scale. It is the cost square curve in dB scale. That's why instead of going varying slowly, it is varying like these near zero values go to very low um, values when you take logarithm, right? Because this is in dB scale. So these are typical things you can expect. So you can expect from data sheets. And um, here is one MATLAB program. Um, okay. So this is the Lorentzian curve, but in dB scale. In um, in linear scale, it will look as something like similar to a Gaussian. It was also shown in the class, I think. And I wanted to show how this the phase is varying from ideally it should have been zero, but with as time passes, this phase varies. So this you can see from a simulation. All of these small steps are taken as normal random variables. And because some of normal random variables are also random variables, so it doesn't matter what time step you take, and they will all act as normal random variables, but their variance will vary. Uh, so that concept you should get. And I'll show you some previously run simulations. So for a line width of 1 kilohertz in 10 microseconds, which is a huge, very long period of time. Okay, so the laser we just saw had 100 kilohertz line width. Right? This is just for illustration. So a constellation point which should have been centered at this 0 point gets smeared like a line, like as a result of laser phase noise. That same 10 microseconds, if you have a 10 kilohertz um, line width, then uh, the constellation point will appear anywhere in this longer range. Again, for 100 kilohertz, uh, this for 1000 kilohertz, which is 1 megahertz. And this is that same small 1 kilohertz value you saw. Uh, this one is plotted for 100 microseconds instead of 10 microseconds. So you have to be careful that in case of a QPSK, for example, you don't want these constellation points to stray into the other decision region. Like you should, the receiver should not confuse the received constellation point with some um, a wrong constellation point. That will be counted as an error, and we don't want errors. Like we want ideally 10⁻⁹ error probability. So these are kinds of how this phase might change. These are all random. and these are called the random walk process. Like each step is a random variable, and the whole process is called random process. That's all I wanted to show today. But uh, do you have any doubts regarding the concepts covered in class? Was I audible? Like,
If you have any doubt regarding the MATLAB or like that Zonek, whatever explain, please please unmute yourself and please ask.
Uh, Sir, can you
So,
repeat?
which part did you have doubts? Like just MATLAB or these equations and stuff?
Yes, sir. Yes, sir. Just MATLAB, sir. Due to some internet issue, 5 minutes. I have joined 5 minutes late.
Okay, I just MATLAB code is generating these plots. I wanted to show you these plots as an example. So ideally, this line you're seeing, can you see this? This line should have appeared as a dot. We wouldn't want any impairments in the transmitter side, but instead of getting a single point, we get multiple points at varying phases. And this thing was calculated for 1 kilohertz line width and total time of 10 microseconds. So this line width is very good, and this total time is kind of long because our optical symbols stay somewhere around 50 picoseconds and things like that, right? So these are um, like this is not just a few symbols. This is a lot of symbols. For the same 10 microseconds, if you have this line width change, then you this constellation will get more smeary. Like the phase will vary over a very wide range. Uh, this is for 100 kilohertz. This is almost covering like if you imagine a QPSK constellation, it is going over to the opposite quadrant almost. And this is for 1 megahertz. This you can expect as uh, a typical laser will have line width close to this. 100 kilohertz was our laser data sheet I just showed that had 100 kilohertz. 100 kilohertz are used in like coherent communication applications also. This 1 megahertz line width, you can see the this constellation points are going everywhere. There are tricks to minimize these errors, but I'm just showing. And the initial 1 kilohertz small line, you remember, when you let that same thing go for 100 microseconds instead of 10 microseconds, this phase error also gets like uh, quite bad. It goes to nearly the other symbols territory. So these decision boundaries you have to be careful about. This is again repeated for like for 1 megahertz. This whole all phases are being covered. Like recovering data from these are kind of tricky, but of course they can be done. And the phase is varying like this. This is a random process. Uh, these are small steps we are taking according to this variance defined by our line width. That sigma square equal to some using this equation we generate these random variables for each step and we let it evolve randomly. So you can see that there are no abrupt changes. It can only vary so much, but like, it can drift quite far. these are other examples for other languages, um, and this for a longer time period. The MATLAB code uh, just generates these like uh, variances defined here. We uh, we used normal random variables of given variance, and sum those up to get the total um, phase error that we are getting. And these three lines are the basic workhorse of the code. Others are just plots and all this. So that's what I showed using MATLAB. I hope I hope it is clear. Coherence time is given by 1 by pi delta f, the line width you use to get the coherence time. The datasheet did not give it, but you can calculate from here. These two equations are sorry. Uh, are these two given in the lectures? I don't remember actually. These two equations, you can easily find them in Wikipedia also, but like
Sir, please, no, sir, these equations are not available. So, can you please share that in which book will able to get read all the stuff?
Kaiser's book. I don't remember full name. Optical fiber communications in
I guess, sir, John K. Kaiser, I think.
yeah, Kaiser, and then there are three books listed. I think Agarwal's book also has some things. So ma'am is combining stuff from multiple books, but the primary textbook is still this Gerd Kaiser.
No, sir,
And
unable to find these modulator formula in senior and in
yeah,
Agarwal also.
Senior is also a good book, but yeah,
So,
this Lorentzian PDF is you can get from this Wikipedia. Just it's not that I mean some core optical thing. Others, I
had you
think you
shared this equation sheets with us?
nope, nope. I was sick
Okay,
the whole last week, so
okay.
um
So, can you please scroll down to upper page? Yes, sir.
yeah,
Just
take
for
screenshots,
some.
yeah, but
Yes, sir.
yeah.
Thank you, sir. Thank you so much.
But like you're supposed to make these yourself when
So
watching this.
actually, sir, some equations I have made, but many this two three equations I'm unable to note it down.
Yeah, yeah, that's fine. I think that's my part.
Anyone have doubt?
Question one in assignment four is
They ask for Zonek P max or V minimum. They difference that ask for that. From that graph they have
okay.
I think I will solve this question. I have include that. Zonek?
Oh, then okay, I'm leaving that.
Yes, yes.
Mm.
It is the formula that you given that that delta f equal to that is square root of equal to that. bandwidth
Yeah.
into delta f into that t time, coherence time.
Okay, then I'll stop presenting it then.
Yes, yes. So if you have any doubt in the MATLAB or anything, you can ask to Zonek.
Sir, sir, I have one doubt based on this bandwidth requirements of laser. Sir, how we can able to avoid the overutilization of bandwidth when we are using this different types of modulator?
Overutilization as in, so
Uh,
when you
bandwidth
send
is
some
the
10
base of.
gigahertz,
Okay, okay, sir. You can proceed, sir.
so when you send some in class also it was discussed like if you send some 10 gigabaud signal, you will occupy uh, 20 gigahertz of optical bandwidth. There is no way around it. You can reduce it by some clever coding that was discussed in the last lecture in this week, I think. Or
Yeah,
but
yes,
but
sir.
but
Yes,
for
sir.
receiving, you don't need the full 20 gigahertz. Like if you're sending 10 gigabaud, optical bandwidth will be twice that. But for receiver bandwidth, you only need half of that. So like for 10 gigabaud, a 5 gigahertz bandwidth receiver is enough. But this overutilization, what you meant, I did not understand properly.
Sir, in a practical real-time scenario, the choice of choosing the proper laser in the application is a very challenging one. So, whether what type of laser is suitable for the application, how we can able to know, sir, by reading the data sheet, or else we have to analyze, do some mathematical calculations like this.
For all practical consideration, laser's own line width will be smaller compared to what you're modulating it with. So, in a optical communication system that you're making using a laser, your modulation should dominate how much bandwidth you're consuming. So these non-idealities, these laser phase noise, these are like problems, but not they won't consume so much bandwidth that you will have to worry about them too much. In LED, yes, you have to worry about LED's bandwidth, but when designing a like optical communication link, you will see later also, I think, that uh,
Okay, sir.
when
Thank you.
you're yeah, so like laser line width was like 100 kilohertz or 1 megahertz, and you're modulating data of like 25 gigabaud, so that is consuming what 50 gigahertz kind of a bandwidth. So your modulation will determine how much bandwidth it is consuming, and that whole thing will have to fit into one grid of ITU specified, whatever ITU is specified.
Okay, sir. Thank you.
Anything else? Any have a doubt?
Yeah, Manish this side. Can you please give me the explanation about the question one that
Yes, yes, yes. That will I include that.
thank you.
I have an doubt in question number two also.
Two. Okay, let's see that. First, I will finish that, and then if you have that doubt, then I will take that also. Or you can write us only. Namita.
Yes, sir.
So these are the questions for you. So I think that we have some only time is very less. So one by one, can you explain me what is the can you from the classroom what you can understand that noise in your laser can be classified? How much the noise type of the noise? If you attend the class and it. What what type of the noise can be occurred in the that lasers? Anyone else can unmute and I can answer that.
So one noise is due to the spontaneous emission.
Spontaneous emission is the one principle of that laser.
Sir, absorption and radiation.
Phase noise. Phase noise, intensity.
Absorption noise and radiation noise.
Okay,
I
one
think
is
phase noise and intensity noise.
yes, phase noise and intensity. Yes, yes. And what is the causes of phase noise and amplitude noise? Why this is happen? What is the reason? In Jonak is also explain you that from the MATLAB
Because of the fluctuation.
fluctuation in
Then change in the angle.
Carrier density fluctuations.
so it will change that amplitude or phase of that.
Phase.
So how amplitude will be changed in that case? Why that amplitude like that? If any signal will have the 5 volt maximum and 5 minus 5 volt minimum, and when we have to receive on receiver, it will be changed like that. 3 volt or 2 volt we have received. What is the reason of that? Okay. Degradation of the consolidation is due to any reason that you have to read that consolidation diagram of the BPSK, QPSK, and that when we send through the receiver any degradation in the consolidation diagram. What is the reason? Define bit error rate. Anyone can define the bit error rate? And if anyone is working in that company, then whatever the accepted limit in the real communication that of bit error.
So bit error rate is the total number of bit errors, transferred bits divided by the total time interval.
What is, again you can something is
Transfer bits, it is the ratio of transfer bit divided by total time interval.
total time interval or total bit will be transferred. How much the bit will be you send on the from the that transmitter and
Yes, so
The total number of bits which have error divided by total number of bits received.
okay. And what is the limit of that in real time optical communication? It is acceptable that bit error. We
To the
can
power of
accept.
9, sir.
Huh?
10 to the power of 9.
Yes, yes, good. So why we not use the direct modulation in for long distance communications? Any reason why? What is the direct modulation and we cannot use for the long distance? You use the external.
direct modulation induces chirp. That's why we are not using direct modulation.
What is the which surf? Which type of surf will cause it due to direct modulation? It is phase, frequency, or amplitude. Which type of surf?
So it is phase.
No, no. It is due to the frequency shift. It is we are not used for the that long distance.
Yes, sir. Yes, sir.
You have already read that even Jonek will also explain that formula of that frequency shift, how to calculate delta.
Yes, sir. Yes, sir. Yes, sir.
So what is the basic principle of that electro-optical modulator? And why we use that electro-optical modulator? Anyone can, if you are working in that telecommunication and optical fiber communication, you have used that component also that in between that transmission line and that receiver. So what is the use on which principle it will be? Basic principle of that.
So the acceptance bit error rate is 10 to the power minus 9, na?
If you take, it will be taken in the log form.
No, no, it's yeah, 10 to the power minus 9. So we don't want. We can tolerate one error in 10 to the power 9 bits.
Yes.
Okay.
So 10 to the power minus 9. Yeah.
So class, any scheme that line coding scheme which we use to group the bits in that. While like that in that digital communication we have that coding scheme. In optical, what is the coding scheme that to group?
QPSK,
Yeah,
QPSK,
QPSK is the modulation technology. It is the coding scheme. How do we code that bit in one that?
NR
That
is it?
yeah,
Non-written to zero, sir.
yes, one is correct. Again, do second one. Anyone else who have no? Return to zero. So Manish, you have doubt in this question or this diagram that you have mentioned that? In assignment 4. So in this class, first that what is the extension ratio and instance loss you have mentioned in one slide that in optical fiber, and what is the significance of the extension ratio in the communications. So extension ratio, yes. Hello. So extension ratio is the ability of the modulator to create the power difference between 0 and 1 state is referred to as the extension ratio. So whatever the signal we have sent, like that it is a pulse, that is square pulse. There is a 1 and 0. Like that this is pi, 2 pi, 3 pi. So it is created power difference with that. What is the power of that P1 and P0? Through which the ratio will explain that what is the extension ratio we can refer as it as this is the extension ratio of that hour. So that minimum output power needed to be necessary, not necessary with 0 watt, because it is possible to district interface due to device no idea. So it is not necessary that we have the 0 milliwatt for the minimum data P0. That power that P0 it is not necessary. One question is also asked in your assignment that we have to calculate that extension ratio, and you have to given that insertion loss that Manish is asked that. Typically, commercial modulator are available with extension ratio between 20 to 30 dB. So, whatever the commercial extension ratio we use, that device are available in modulator, we have the 20 to 30 dB. Higher the extension ratio, better would be the depth of modulation. If we have the more number like that, 30 dB the extension ratio, modulation will be more. So it will be we have the less noise in that signal, and we can extract that input of the signal at the output receiver with that actual signal in that case. So instance loss of the modulator quantify the power loss in the modulator. So we have like that, we have sinusoidal signal sent through the optical fiber, and it have the power input power of like that 100 milliwatt, and at the output side we receive P out only like that 10 milliwatt. So 90 milliwatt will be lost in that case in through the fiber. Okay, so through this we have to mention that what is the insertion loss in the optical fiber. We can measure that through the insertion loss, and it will we have needed it is very less in the that optical fiber. Second question is that an electro-optical modulator such that voltage is applied on the one of the arm. Like that we have the modulator. So we have applied a signal E1 and E2. This is input and this is our output. So we have applied only one, that E1 signal we have applied, E2 equal to 0 we have to keep it at a 0 on one arm. One of the two branches of the interferometer has a loss. We have the loss, that the insertion loss equal to between the 0 and 1. So that output field equation that Jonek have mentioned one equation to about you, that loss is also that. So E equal to 0.5 EJ phi 1, that phi 1 is the phase of 1, that this is phi 1, and this have the phase of phi 2. plus n is j phi 2. J phi 2 is the imaginary part, and this one is that imaginary part there, right? And en is the input, that signal of input. Find the extension ratio as a function of that insertion loss. Extension ratio is defined the ratio of maximum output power and minimum. I already explained that. So this is equations. So output power is directly proportional to square root of that output of the signal. So it is given that input square root input by 4 but plus 1 upon insertion loss into e की power minus j phi square of e की power j2 phi. So first we take that if that phase is equal to 0, that change in the phase is equal to 0, in that case with phi 1 is equal to 0 we have put that e plus 1 upon n square it will be given. Second we take upon maximum phase, like that we have the signal 0 to 1 and this is the our signal will be passed like that. So this is the 0 phase, this is the pi, this is the 2 pi, this is the 3 phi, and this is the phi, delta phi. So first we have take the 0 in case that signal that our phase is 0, and second is that our phase is opposite at 180 degrees move. In that case we have given p minimum equal to 1 minus n square. So we divided extension ratio is like that p out 1 upon p minimum, because extension ratio is a p out 1 upon p out 0. In case of the 0 we have not to restore any signal, that phase will be 0, it will be direct, it will not modulate with the 180 degrees Celsius. Whatever the we have the input, it will receive at the output side. It will not change the phase of that signal. So it will be like that 1 plus neta upon 1 minus neta square. I think that Manish, this question you have asked, that you have doubt in that case.
Correct.
Okay.
Yes, sir.
So we have the given that laser. So laser have dial emit 100 milliwatt constant optical power. So that P of actual P is equal to 100 milliwatt. So what is in case of the phase noise, we have the fluctuation in power. So P equal to what is our case? P out plus delta F. So change in the fluctuation in that case of the total power we have received, some fluctuation will be in that case. So this is the spectral density of that signal is 1 minus 120 dB per hertz. So find the largest possible electrical bandwidth in megahertz, so that our root mean square optical power fluctuation is less than 0.1 milliwatt. So we need that delta F should be less than equal to 0.1 milliwatt. Okay. So this is the power density you have to given. Spectral density we have convert into 10 to the power 12 dB, because it is in the log form. So P in equal to 10 log of that power spectral density R in. So we have taken that 10 to the power 12, this 120 will be go to 12 and 10 will be cut by that. Hello?
Yeah, correct, sir. Understood.
Okay. So we have given P equal to 100 milliwatt or delta P equal to 0.1 milliwatt.
Correct.
So whatever that Zonek you have given that one question, that formula also. So change in that fluctuation in the phase, this is phase noise. So delta P by P equal to square root of indicator of F1 to F frequency SI upon F. So 0.1 delta P we have given 100 milliwatt, we have to given P. That will we have to, if you solve this, ma'am have solved in this or in the classroom also. So SI will be the spectral density of that signal. So we can return it bandwidth into spectral density 10 to the power minus 12. So bandwidth will be given square root it will be in a square and it will be divided. So it will become equal to that 10 to the power minus 3 ka square upon 10 to the power minus 12. So it will give you upon 10 to the power 6 hertz. It will be around 1 megahertz. Manish.
Correct, sir. Understood.
Okay.
Thank
So
you very much.
it will given that in the equations and formula in that classroom also, that video or that YouTube video also, ma'am.
Yeah.
So commercial Mach Zehnder modulator work on principle, anyone that? So the operation principle of that, this is the Mach Zehnder modulator. So we have the two modulator, that microwave detector, this electrode, one electrode and second electrode. So this is the modulator's frequency, that phi 1 and phi 2. we have provided a E1 and E2, and V1 signal applied in this, and output side we have to ground both the signal mode electrode, and this is that output of power. So we have that y-axis equal to P to Pn, and we have that signal. This is the quadrature point, and this is the 0 point. I have already one equation I have explained in this case. So the operation principle is based on the electro-optical effect. So what is the electro-optical effect? It will make out the material which change the refractive index of the data. Like that, we have the fiber. In this case, this is the fiber. This is the modulator we have to apply, and there is we have the signal. So it will change the refractive index of there. This is the material which made of that optical fiber. So it will change that signal refractive index, this fiber. So if the refractive index will be changed, that signals numerical aperture fiber will be also changed, and it will affect that output of the signal also. So what is the characteristic variation in the optical causing the change of the refractive index of the modulator of the arms? So we change that this arm, we change the modulator of that refractive index. So variation of refractive in the modulator arm induces change of the material propagation constant beta. So beta propagation we are defined by 2 pi upon lambda. So if it will be changed, then lambda will be changed also, that wavelength will be changed of that signal also. Change of material resulting in a different phase in the both the modulator arm. So if one signal will go through this and one signal will go through this, so it will change the phase of that signal. The input optical signal is divided by the 3 dB couple into equal parts in lower and top. We always mention the signal in the 3 dB measurement in every time. The external modulator divided by the electric signal with corresponding data rate. We have the external modulator also. So if no electric field applied in the both the signal arm, it arrive the same phase. If we applied E1 equal to 0 and E2 equal to 0, it will arrive in the same phase. Whatever the input signal will receive the output signal. Depending upon the phase difference between the MJ and the signal can interface constructive distortively. So whatever the phase difference is here, if it is a pi and pi, it will match the constructively. If it is 0 and pi, it will match the destructively. If the one signal is like that, it is same signal, then it will modulate like that. If it is opposite phase, then it will like that, interface like that. So it depending upon that phase difference, we have to apply delta phi 1 and delta phi, that we have to receive the output like that constructive signal or that destructive signal. One question that Anjali maybe is there, that he asked that what is that coherence laser time that. So find the phase error accumulated over the one symbol slot. So if the one symbol slot is like that, we have sending the symbol like that in NRZ or RZ form. Like that we have the bit of 0, 1, 1, 0, 1, like that. It is one symbol form we have to make for a 24 gigabit transmission line. It is the bandwidth of the transmission line or frequency of the transmission line is 24 gigabit. If the spectral bit is 10 megahertz, so delta F we have given equal to 10 megahertz. Right, we have to calculate that, find a phase accumulated error, phase error delta phi, and we have given to delta F. So we have tau is given equal to already that John delta F upon delta F. From that we have calculate tau. So F board we have to given in the form of the F board. So we have to change it in the frequency into that time scale. This is tau. So it will 25 into 10. This will come to 40 picosecond. 1 upon 25 25 into 10 to the power 9 gigabits. So we have to calculate T board down like that. So spectral bit delta we have to given that 10 megahertz. So the error interface equal to 2 pi delta V into T baud. It is 2. So 2 pi into delta V already given T baud we have calculated from the transmission line capacity. So it will around given that 28.28 m radiation. So from radiation to degree we have multiplied with the signal with the 180 into pi. So it will given the form into degree there. So it will give around 1.6 degree. So this is from my side. So now you can ask your questions.
In question number 6, I think the options are same, it seems, sir.
In assignment.
Yes, sir. BPSK modulation can be achieved by
In assignment,
Yep, looks like a mess up from my side.
I think first and second option is same options, and third and fourth looks like same.
in 1 minute we can look into that. Question number 6, that BPXA modulation can be achieved by this one, na?
Yes, sir.
So you said that first and
Second options looks like same, sir, and third and fourth looks also same.
yeah, in one case it will be 2 pi. I think that both the case, one is V pi and second is in the swing voltage is 2 pi. Jonek?
Yeah, it should have been, but while configuring the questions, there is a mess up, of course. So everyone will get this point. So
We will check that. We can report that.
yeah.
Yes, yes.
Yeah.
Anything else? Namita? Namita?
Unable to understand the question number second. Even Sonak sir is also try to, but I am unable to
This
understand the
one.
question number second. Yes, sir.
Lawrence will full fit that formula. Lawrence full fit he given for that, na?
Yes, sir.
Lawrence, this data will be missed for question 2 to 5. This is the delta psi m, like that they have given that. Psi half it that they have given 10 megahertz. And delta that is spectral with that f
Okay,
body
sir.
minus 20 dB, so you can convert and that. Lawrence? Jonek?
Yeah. No, Kushagra, it's okay. Who's from physics background? I'm from electrical, so electro-optic effects is
No. Actually, in that
lithium ion.
assignment, I think there's some data they are using the following data about question to 2 to 5. Some this data, I think.
No, like that is from Lorentzian shape. It is given. So use that Lorentzian formula. So a power output as a function of frequency is given.
Yes.
Like not power output, is power spectral density as a function of f is given, and instead of like they're saying that the full width of half maxima, which
Yes.
is half the peak power, happens where like the full width at half maxima is given, and you are asked to find out where this
Spectral.
full width at not half maxima but 1/100th of the maxima.
That formula
Where
you
that
that
occurs.
formula you mentioned, that Lawrence PDF, that will be work on that estimate. Lawrence PhD that or spectral density.
Yeah. The shape is described by this Lorentz PDF of course. Yeah. Like,
So
you can
Namita,
just
you
look it
can
up
try
and
with that one. If not possible, then write to me that.
it's some
Okay,
like
sir.
algebra like manipulation.
Namita,
Sir, actually, I'm unable, like, in this, I have to see, like, F and F naught for using that PDF formula.
yes. So,
Okay, sir, I'll try
sir,
it once.
from that formula that Lawrence, that Jonek have given you that in the class
Yes,
na.
sir.
If you have any doubt, then write to me in the classroom or that anything in a email we can.
Okay, sir.
Okay.
So F naught you will not need because like everywhere F appears along with F naught. F minus F naught is the only form where it appears because F minus F naught whole square kind of terms appear. So you won't need F naught, and like because it's a quadratic equation, you will get two frequencies. I don't think it should be too difficult. It's just algebra, like, just manipulate things.
Okay, sir.
I think
And
Lawrence,
yeah, I have been sick last week, and then before that I was slacking. So like the course discussion forum is lying kind of dormant. I will get shouted at by ma'am tomorrow, but anyway, uh, keep posting there. You can get the get to the course discussion forum by going to the this. There is a ask a question button at the top bar of the NPTEL course page. You can post your questions there. All of them will be answered, of course. But yeah, I was too sick to answer. So that's not answer. And also, you don't have to wait for me. Like, if you understand something, you can also answer. If it is wrong, we'll correct it. Use the discussion forum.
so any have any doubt then? So Jonah, can we finish that?
Ask my question. Did you able to get the answer of my question? Like how many signals can be transmitted in a single optical fiber?
I did not even look the numbers. So 50
Okay.
gigahertz, there are these many bands, and in C band, and then voice signal will be something like 64 kbps or something. But like, let me. I have not looked, so I will answer. Okay, next time maybe.
Okay, sir. Okay, sir.
Sorry.
Okay, sir. No problem, sir.
Namita, definitely we will reply you. No problem. We have to discuss with the ma'am and then we have. So
Okay,
Jonek,
sir.
can we finish that?
I guess.
So tomorrow, Jonek, I will busy some my lab work, so maybe not able to join meeting. That.
Okay, okay. And just tell ma'am.
Okay, okay. So any mail option of that ask two questions, Jonek? They have to.
I think I can see your questions. Shri Harshita. It's showing the Shri Harshit something. Dot dot dot. I will
Okay.
answer like starting tomorrow. I'm answering all of this. Don't worry.
Okay. Thank you everyone for that. So if you have any doubt, then you can ask to that from ask to question that, or you can write on that classroom. Also, I have created. You have already joined that also. So
Yeah, I
next.
prefer classroom and this
Yeah,
forum, not
ask to question
WhatsApp.
that both. First, you mention that ask to question that also that yeah. You can mention also that Google Classroom, so we can take your questions and maybe put on the next class also that.
Okay, sir.
Okay, thank you everyone.
Thank you.
Thank you, sir.
Thank you.
Next